Welcome to Rediscovery, where the wonders of space and science ignite. The Sun, our very own star. It's a giant ball of plasma, a churning sea of charged particles all engaged in a cosmic dance of energy and light, and just like our Earth, the Sun spins on its axis. But unlike Earth, where the entire planet rotates at the same speed, the Sun's rotation is a bit more complex. The Sun doesn't spin as a single solid object. Instead, different parts of it rotate at different speeds. This phenomenon, known as differential rotation, is key to understanding the Sun's magnetic personality. It's like a cosmic blender, with the equator spinning faster than the poles. This difference in rotational speed has profound effects on the Sun's magnetic field, a force that extends far beyond the Sun itself, influencing the very nature of our solar system. Imagine a line of dancers all holding hands moving in perfect harmony. If the dancers in the middle start spinning faster than those at the ends, the entire line begins to change. The line will twist and turn, creating intricate patterns that are mesmerizing to watch. This is similar to what happens with the Sun's differential rotation, a fascinating cosmic dance. The equator spins with a quicker tempo, completing a full rotation in about 25 days, much faster than other parts. Meanwhile, the poles take their time, leisurely finishing a rotation in roughly 36 days, almost a week and a half longer. This difference in speed isn't just a cosmic curiosity, it has profound implications. It's the engine that powers the Sun's magnetic dynamo, the complex process that generates its powerful magnetic field. As the electrically charged plasma within the Sun churns and flows at different speeds, it creates electric currents that are vital. These currents, in turn, give rise to magnetic fields, much like the flow of electricity in a wire creates a magnetic field around it, driving the Sun's dynamic behavior. Deep within the Sun, beneath its blazing surface, lies a region known as the convection zone. Here, hot plasma rises from the Sun's core, cools, and then sinks back down, creating a constant churning motion. This churning, coupled with the Sun's differential rotation, sets the stage for the solar magnetic dynamo. Think of it as a cosmic generator, powered by the Sun's own rotation and internal heat. As the plasma in the convection zone flows and interacts, it stretches and twists the Sun's magnetic field lines. These lines, like rubber bands, can only be stretched so far before they snap and reconnect in new configurations. This process of stretching, twisting, and reconnecting amplifies the Sun's magnetic field, creating regions of intense magnetic activity. The Sun's magnetic tapestry loops, spots, and fields. The Sun's magnetic field isn't uniform. It's a complex and intricate system that varies greatly across different regions of the Sun. It's a dynamic, ever-changing tapestry woven from magnetic loops, sunspots, and vast magnetic fields that extend far into space. These magnetic features are in constant motion, interacting and evolving over time. These features are not just visual spectacles, they are signs of the immense energy and activity constantly taking place on the Sun. Solar flares and sunspots are direct evidence of the powerful forces at work. One of the most striking manifestations of the Sun's magnetic field is the appearance of sunspots. These dark patches can be seen forming and evolving over days and weeks. These dark, cooler regions on the Sun's surface mark areas of intense magnetic activity. They are significantly cooler than the surrounding areas, making them appear darker. Think of them as magnetic knots, where the Sun's magnetic field lines are so tightly wound that they inhibit the flow of heat from the interior. This results in the cooler, darker appearance of sunspots. These sunspots often appear in pairs like opposite poles of a magnet, connected by arching magnetic loops that extend into the Sun's atmosphere. These loops can stretch thousands of kilometers, creating a bridge of magnetic energy between the spots. The solar cycle, a heartbeat of activity. The Sun's magnetic activity isn't constant. It ebbs and flows in a cycle that lasts approximately 11 years, known as the solar cycle. During this cycle, the Sun's magnetic field undergoes a complete reversal, with the north and south magnetic poles switching places. The solar cycle is like the Sun's heartbeat, a rhythmic pulse of activity that affects the entire solar system. At the peak of the solar cycle, known as solar maximum, the Sun is at its most active. Sunspots are more numerous, and solar flares and coronal mass ejections, powerful bursts of energy and charged particles, are more frequent. These events can have significant impacts on Earth. disrupting communications, affecting satellites, and even causing power outages. Solar reach, Earth and beyond. The Sun's magnetic influence extends far beyond its visible surface, encompassing a vast region called the heliosphere. This bubble-like region, carved out by the solar wind, a constant stream of charged particles emanating from the Sun, protects us from harmful interstellar radiation. But the Sun's influence can also be felt closer to home. When solar flares and coronal mass ejections erupt from the Sun, they can send a barrage of charged particles towards Earth. These particles interact with our planet's magnetic field, creating stunning auroral displays, the northern and southern lights. But these geomagnetic storms can also disrupt our technological infrastructure, affecting satellites, GPS systems, and even power grids. Unlocking the Sun's secrets, prediction and protection. Understanding the Sun's magnetic field and its behavior is crucial for protecting our technological infrastructure and ensuring the safety of astronauts in space. The Sun's magnetic field is a complex and dynamic force that influences space weather, which can have significant effects on Earth. Scientists constantly monitor the Sun using a variety of ground-based and space-based telescopes, studying sunspots, solar flares, and other solar activity. These observations help us understand the Sun's cycles and predict its behavior more accurately. By analyzing this data, scientists can track the Sun's magnetic activity, predict solar storms, and issue warnings to satellite operators and power grid managers. These predictions allow for timely precautions to be taken, minimizing potential disruptions. These predictions are essential for mitigating the potential impacts of solar storms on our increasingly technology-dependent world. Solar storms can cause geomagnetic disturbances that affect communication systems, navigation, and even power grids. As we venture further into space, understanding and predicting the Sun's behavior will become even more critical. Future space missions will rely on accurate solar forecasts to ensure the safety of astronauts and the success of interplanetary travel. The Sun, our life-giving star, is a constant reminder of the power and beauty of the cosmos and of the importance of continued scientific exploration. By unlocking the secrets of the Sun, we not only protect our technology and astronauts, but also deepen our understanding of the universe. Thanks for watching Rediscovery, where every journey uncovers breathtaking wonders. Craving more thrills? Smash that like button, drop a comment, and hit subscribe. Let's continue exploring the unknown together.